Hi everyone. Looks like there are some issues with Joseph's mic. So give us a couple of minutes and we'll get started.
Okay, is this better? Can anyone hear me?
Yeah.
Okay, great. So sorry about those technical difficulties. But yeah, it's a little early for me here. It's about 2:30 a.m., but I think we're good to get started. And yeah, so this will be a pretty quick recitation. So I'll go over a little of the motivation behind how we're setting up problems involving variational autoencoders, and then Shot will go through the code. So I'll share my screen here and let us know if you have any questions. All right, can you see my screen?
Yep.
Great. So we'll look at this example here. And yeah, so like I said, in this recitation, we'll be looking at variational autoencoders, how they're used in unsupervised learning problems. We'll look at the example of where uh, we're using the variational autoencoders to learn latent distributions needed to reconstruct images. So I'll say that again. We're using variational autoencoders to learn latent distributions needed to reconstruct images. So there's two objectives there, right? One is we want to learn the latent distribution, and then the other is we want to learn to reconstruct the image. And in other words, we want to know how much the does our latent distribution deviate from a standard normal distribution, and how much does our reconstructed image deviate from the standard normal distribution. We'll use two loss functions that we talked about in lecture. One was KL divergence. So KL divergence is what we use to measure how one distribution deviates from another distribution. And when we're looking at how one image deviates from another, there's two popular ways of looking at that. We can look at mean squared error, right? The error between the two images, or we can use binary cross entropy loss. So if you look at each pixel with respect to each other, that's how we might want to use the loss of the image. And then the sum of the loss between the pixels is our reconstruction loss. So yeah, as you'll see, there's the encoder, right, which is used to derive the latent distribution. And then there's the decoder, which uses which reconstructs the image using the latent vector sampled from the latent distribution. So the idea of an encoder is not new. It's simply a multi-layer perceptron or convolutional neural network, depending on how you want to think about the problem. And the decoder is nothing more than a reflection or a mirror of the encoder. And in lecture, we talk in detail about the math behind forward and backward propagation. We also go over the motivation behind what's called a reparameterization trick, which is how we get this latent vector from the latent that to solve these unsupervised learning problems. But yeah, those are the key things to set up the variational autoencoder. And without further ado, I'll let Akshat show what these core components look like in the code when implementing the variational autoencoder.
Right. Thanks, Joseph. Uh, I hope I'm audible. If I'm not, please let me know.
Yeah, loud and clear.
Okay. So, yeah, thanks again, guys, for joining us so early in the morning. I'd like to start with doing a code demo, very short for autoencoders, and then kind of show what's the difference between VAs and autoencoders. The code looks relatively similar, but there are subtle differences which are actually quite major. Uh, but yeah, before I do that, I'll quickly just show you what an autoencoder architecture is supposed to look like. So one second. Right. So, an autoencoder architecture, very simply, is something of the sort that you have an input, which could be an image. Let's take the example of an image. And we have uh, an encoder network, which in some sense creates a low dimensional representation of the input into a latent vector, which is of our chosen dimension. And so this is me talking about autoencoders right now and not VAEs. And then we have a decoder network, which takes as input the latent vector and produces or aims to produce back the input that went in. And the aim here could be to minimize the mean square loss between the input and the output that comes out of the decoder. So that's very simply put what an autoencoder does. There are multiple applications of autoencoders. One could be compressing the high dimensional input into a lower dimensional, into some kind of lower dimensional representation. The other one could be capturing the most important components of an input. And again, the idea becomes very similar to PCA, that you want to send some features into a neural network. So you want to send only the most representative um, features in. And those are some of the applications of autoencoder. So I'll quickly show you how an autoencoder looks like in practice in a in code. So yeah, so this is what an autoencoder code looks like. It's very simple. It is made up of two networks, the encoder, which is a bunch of linear layers. I'm working with MNIST images here. So the starting input dimension is 784, and I'm compressing it to the encoder output latent vector compressed vector, which is of 10 dimensions, which is a very natural dimension to compress MNIST images, which are digits from 0 to 9. And then there is this decoder network that recreates or tries to recreate the images from the 10 dimensional input. And the here's the forward network, where which kind of tries to which is just basically going through the forward pass and the backward, sorry, which is basically trying to go through the encoder and the decoder. And sometimes, well, when you're training, you're sometimes you want to use the encoder only to encode images. Sometimes you want to use the decoder. When you're training, you're using them both. And that's kind of what these if conditions are. And yeah, and this is how the reconstruction in the original images look like. So this was the original image, and this was reconstructed from a 10 dimensional compressed vector. And yeah, that's what an autoencoder looks like. uh, Next I'll show you a VAE, and it looks relatively similar in terms of how the code looks like, but there are very important differences that are like we should there are important differences that don't look as important in the code. There's just few lines, but they're really important. And that's the entire difference between VAs and autoencoders. So just a quick, again, a quick motivation to VAs. So as Joseph kind of um, pointed out, what we want to do now in VAs are to be able to, so given our data set, to be able to, and our data set belongs to a particular distribution, to be able to generate data from the same distribution that our data set belongs to. And that's kind of the aim there. And again, we have, uh, as Joseph showed, two networks in VAs as well. So what we have is X, let's say X, which are our training samples, and are they belong to or come from a probability distribution of some unknown distribution which we have no idea about. But if we did, we'd be able to sample from that distribution, and that's what we want to do in VAs, is to in somehow try and get access to this distribution Px. But this is quite difficult to do. So what we do is we create a network that looks similar to an autoencoder but does something that's very different. So we take the original image, um, and here's the encoder network. And the job of the encoder network is to in some sense create a is to project the data into a latent vector space, and to project uh, the data into a latent vector space is basically the encoder should give us the uh, defining characteristics of a distribution. And what are the defining characteristics of the distribution? They can be, if the distribution is Gaussian, they can be mean, or they can be a covariance matrix. And that's kind of what comes out of our encoder. So in an autoencoder, what came out was just features. So feature values of inputs. But what comes out of an encoder in a VAE are the parameters that describe a latent vector distribution. So the parameters would be mu and sigma. And this latent vector space is something which we define ourselves, which we choose ourselves. So in VAs, or in vanilla VAs, we choose this latent distribution to be a Gaussian. So the parameters that correspond to a Gaussian are the means and the covariance matrix. And we also assume that the Gaussian distribution has uh, is diagonal basically. So what you can expect to come out of the encoder is, let's say my vector space is 4-dimensional. So you can expect that we get an 8-dimensional vector, which kind of describes that latent distribution. And in the decoder, the job of the decoder is to be able to generate back the data given the latent vector, which is sampled from this distribution. Now, then there's a lot of math that goes in that P of Z of X. This is something we cannot find. So we try and approximate this with another function, P of Z of X. And then to be able to train this encoder network, we want to minimize the KL divergence between the two. And what we end up doing is we end up minimizing a loss, which is the same as minimizing the KL divergence between this function Q of C of X and P of C. And we want to also minimize the reconstruction error. And the reconstruction error depends, the loss function that we use to define the reconstruction error depends on the underlying distribution that we choose. If we choose a Gaussian, then this would be a maximum likelihood approximation, and we would end up using mean square error. If we have a Bernoulli distribution, we end up using a cross entropy loss. But yeah, that's I think something that Bhiksha covered in lecture, and that's a lot of steps of math. But this is what our loss function looks like, and these are, in my opinion, the two major differences between an autoencoder and a VAE. One is that the encoder is producing not a compressed version of the image, but the parameters of a latent distribution. And the second is the loss function, which is not as simple as doing mean square error. So with that, I'll show the code, but uh, before I do that,
I would like to pause for any questions if people have any. All right. So let's look at the code. Yeah. So what a VAE looks like. It'll so the definitions of the encoder and the decoder networks are very similar. I've chosen a latent vector dimension of size 16. Now, 16 means there are the mean is a 16-dimensional vector, and so is the covariance matrix, which is 16 times 16. So the encoder network has outputs 32 variables, and the decoder network then samples from our latent vector space and tries to recreate um, the image with the aim of not reconstructing the image, but sampling from the distribution from which our data came from. The forward is now different from an encoder, where it's just not passing things through the encoder and then recreating them in the decoder. What we have is we uh, pass things through the encoder layers, and the output that we get are now the parameters of a distribution. And the first 16 elements are correspond to the mean. The second 16 elements correspond to the uh, variances, and the next step is to, well, after this we kind of come here where we sample from the distribution um, using the reparameterization trick, and using this latent vector we create uh, an image which we, through our loss function, uh, aim that it comes from the distribution that our data came from. So um, first difference to highlight is that what's being generated are parameters of a distribution from which we sample. And then the second difference is loss function, which is in this case a binary cross entropy loss and the KL divergence. And this is the we've assumed the underlying distributions to be Gaussian, and this is what the KL divergence of a Gaussian distribution between a Gaussian distribution and a zero mean unit variance Gaussian distribution looks like. And that is it. So these are the two main differences. Whereas if you look at in an autoencoder, what the loss function looked like was it was just a mean square error loss. So yeah, and uh, so the networks kind of trained, the loss reduces, and we can sample from the latent vector distribution that we just learned in some sense. So that's that's a VAE. Uh, yeah, so that's basically it. And again, feel free to ask any questions that you might have. Uh, well,
Yeah, all right. So I know that was a short recitation, but sounds like everyone understood what's going on. And I think that, yeah, if you're able to understand the core of this is what the data looks like, what the model looks like, forward propagation, loss calculation, backwards, and then optimization. That's the core of the neural network, and it's not too different than the other neural networks we look at, except the objective is different. And yeah, so good stuff. Thanks, everyone.
That marks the end of the recitation. We'll put up the notebooks on the website, and we'll stay on for another, as long as everybody leaves. If you guys have any questions, feel free to stay back and ask.